Here's number one. It tells us that we have a ball that strikes the ground and it rebounds, and it wants us to find the change of linear momentum of this ball. Well, to start this problem, I'm going to write what I know, and I know its mass. So mass is 58 grams, which is 0.058 kilograms, and tells us that it's moving at 32 meters per second when it strikes the ground at an angle of 42 degrees. So that angle will be this one here. I'll call it theta 1, and I'll call this V1, which will be 32 meters per second. And I'm going to break it into its x and y components. And its y component is V1 sine of theta 1. Its x component is V1 cosine of theta 1. And then its final velocity, I'll call it V2, is 29 meters per second. So here. And its angle is 38 degrees. It'll be this angle here. And I'll call this theta 2. And again, I'll break it up into its x and y components. Its y component will be V2 sine of theta 2. Its x component will be V2 cosine of theta 2. And now I'm just going to say what direction is positive and what direction is negative. So I'm just going to say that right is positive, left will be negative. I'm going to say that up is positive and that down is negative. To solve for the change of linear momentum, I will use the conservation of momentum equations. And one of these equations is that delta P is equal to P final minus P initial, where P is momentum, which is equal to mass times velocity. So I'm going to treat the x and the y separately for this problem. So the x, we'll say that delta P in the x is equal to P final in the x minus P initial in the x. Now the final momentum in the x is here. It'll be mv2 cosine of theta 2. So I'll say delta P in the x is equal to mv2 cosine of theta 2. And the initial momentum in the x is v1 cosine of theta 1 times mass. So it'll be v1 cosine of theta 1. So that's it for the change of momentum in the x. The change of momentum in the y is delta p in the y. It's equal to p final in the y minus p initial in the y. So it's going to be equal to the final momentum in the y is mv2 sine of theta 2. So mv2 sine of theta 2. Now this would be minus for the initial momentum in the y. But since we said that this is negative over here, we're actually going to write positive mv1 sine of theta 1. It's always very important to make sure you're accounting for what direction the ball is traveling on, the initial and final for it. Otherwise, you will just get the problem wrong. So you should always pay attention to how it's traveling before and how it's traveling after and account for that negative. So I'm going to use the Pythagorean theorem to find the magnitude over here of the change of momentum. So I'll say delta p, the magnitude, delta p is going to be delta p in the x squared plus delta p in the y squared. So I'll write this whole thing squared. It'll be m v2 cosine of theta 2 minus m v1 cosine of theta 1, this whole quantity squared, and it'll be plus m v2 sine of theta 2 plus m v1 sine of theta 1, this quantity was squared. So that's the equation to find the magnitude of the change of momentum and to find the direction of this. I'm going to have to do something a little bit special. So when you calculate delta p in the x, it'll be some small negative number, which just means it's like the change of momentum will be some small thing here. And the change of momentum in the y will be some larger thing that'll be positive. So this will be your vector for change of momentum, the direction. So you have to find this angle here because it tells you an angle with respect to the ground, and you want to match that. So I'm actually just going to find this angle here and add it to 90, which would be that angle there, to find my angle with respect to the ground. So I'm going to draw a vector going up This will be delta p in the y. And then the vector going to the right, this will be delta p in the x. And then here will be delta p. So I'm going to find this angle. I'll just call it theta. And ultimately, I want to say that theta 3, which is the direction of the change of momentum, will be equal to this theta, which I'll calculate, plus 90 degrees. And this will give me my final answer. So to find this theta, I'll use inverse tangent. So I'll say that tan inverse is delta p in the x over delta p in the y. When you calculate delta p in the x over here, you'll get a negative number, but in here you should plug in a positive number because you'll get something like negative 1.3 degrees, and you want positive 1.3 degrees. So just plug in a positive number for this x, and y is already going to be positive. And this will be equal to theta. So when you find this angle theta here, and you add it to 90 degrees, you'll get the final direction of your change of momentum vector. That is your final answer.